Hi everyone. I keep receiving some very interesting questions on my email and on LinkedIn. I don't have time to answer all the questions, but occasionally there are some very interesting questions which warrant a video. Mostly these questions are tied in with some applications, which is why occasionally I pick some questions and try to make videos on them. Okay, you'll also get to learn some interesting applications of those circuits. So, this example is one such circuit. On the face of it, it looks like a very simple circuit. You have a differential NMOS input pair. You have a low voltage signal which goes from 0 to 2 volts and a complementary version applied to the other half. Okay, if this is going to 0 to 2, this will go from 2 volts to 0 volts applied to an NMOS differential input. On the load side, you have a PMOS cross-coupled load. Okay, so what is this? We will briefly discuss it when we discuss the operation of the circuit. Okay, it's a regenerative latch, but only a PMOS side is regenerative. Okay, so it's a PMOS cross-coupled latch. The interesting thing here is you have a PMOS device with a gate connected at 15 volts inserted between the load and the input pair. You are supposed to find out what is the output voltage of the circuit. Now, before we analyze the operation of the circuit, I'll first briefly talk about its application and then we'll try to logically arrive at the structure. The application for this circuit is what we call CMOS level shifters. So generally, if you take digital systems like microcontrollers or microprocessors, generally they will be usually a part of a big system. And in that system, those microcontrollers or microprocessors, they might be driving other high voltage devices, other high voltage chips. Okay, example included an LED driver, or it's a driver for some motors. Okay, so for these circuits, they will need higher voltage levels to control them. Most of the control signals will all be generated inside these processors or the microcontrollers. But when they are transmitted outside the chip, they have to be sent out as high voltage signals. And I've already told this, any given technology, you get different flavors of devices. Okay, you will get low voltage devices, you get high voltage devices. So typically low voltage devices operate at the lowest voltage in the technology, also called as core devices. High voltage devices will operate at the higher voltages. Okay, and then you'll also get some flavors of devices which will operate on voltages between these two levels. Generally, we perform all the complex mathematics or complex calculations and computations, and you generate all the control signals on the core level itself using the core devices, because core devices operate on the lowest supply voltages. Therefore, they give you all the benefits of technology scaling, right? Lower voltage means lower power, and you also get higher speed because of lower capacitors. Okay, so that you reap in all the benefits if you perform all the computations on the core devices. Finally, when they go to the external world, you just somehow change those levels. The core voltage signals, let's say, go from 0 to 1 volt. You try to change them to 0 to 5 volts and transmit them. So that intermediate circuits, which is between the input output and the core devices, core part of the microcontroller or the microprocessor, is what we call level shifters, CMOS level shifters. So the circuits which will take a 0 to 1 volt input, a low voltage level input, and create a high voltage level output. And it will be the same. You won't change any data. It will just be the same replica, the copy of the same data, but they will now be transmitted with higher voltage levels. Okay, so that's the application. Now, how do we do it? So keep in mind, a core generally is a static CMOS circuit, CMOS circuit with zero static power dissipation. We would expect the same thing in level shifters as well. So we need to design level shifters which will offer us zero static power. So one obvious thought process is that, can we use a CMOS inverter itself to get the zero static power? So we'll see. Let's apply a 0 to 2 volt and let's assume the high voltage is 5 volt. I'm connecting the inverter to a 5 volt supply. Let's say we feed 0 volts. If I feed 0, NMOS is turned off, PMOS will charge this node fully to 5 volts. So we don't have a problem. We have generated a high voltage. The problem arises when the input is high, that is 2 volts. And let's assume the input level is high enough to turn on the NMOS. It's greater than the VT of the NMOS. So these two devices will be high voltage devices. Okay, we have built the CMOS inverter using a high voltage device. I'm assuming that the VT of these NMOS devices, of the NMOS device, is lower than the higher voltage of the input signal. Okay, the V high voltage of the input signal. Now, the problem here is that compared to a conventional CMOS, one path is usually turned off. But here, when you apply a 2-volt input, the PMOS gets sufficient VGS. In fact, it gets more VGS than the NMOS. Now, I can do one thing. I can make the PMOS strong. I can size it really large enough and try to bring this node voltage lower and lower. But still, I will not be able to bring it to 0. And the important point is there will always be a static power dissipation, which is directly flowing from supply to ground. If the input is says at static 2 volts, you are going to draw a DC current. So even though the circuit, you might make it work, it resembles the operation of a pseudo NMOS logic with a resistive load or a PMOS linear region load. You might make it work, you might bring this low voltage as low as possible, but you will still end up having static power dissipation. That's the problem with using a conventional CMOS inverter. So what we go for is a modified circuit. This is what we call a CMOS level shifter. What does it do? How does it avoid this problem? We'll get to know that when we analyze the circuit. One thing immediately you can see is that the problem was that we were connecting this 2-volt signal directly to the gate of the PMOS. Okay, therefore this PMOS, there was a charging path always from the supply to the output node. The PMOS was never turned off. But here if you see, we have a separate cross-coupled load whose none of the inputs are gates or control signals are coming from the input. They are generated from the output itself and fed back to them. Okay, so you can think about it. Okay, that's one way of thinking that maybe you don't have this problem that we were seeing in CMOS inverters. Okay, direct path from supply to ground. To analyze the circuit, it's easier to analyze this. I'm assuming you don't know this, so I'll just explain it very briefly. Let's assume initially the voltage is at 0. This input voltage is at 2 volts. And because this is at 0, this is at 2 volts, this node would have gone to 0 volts. This node would have gone to 5 volts. Okay, it's a CMOS inverter, so you can think about it. If this gate is at 2, the drain should be at 0 volts. So you can look at it that way. Let's assume this is at 5 and analyze the circuit after. Now the input has gone from 0 to 2 volts. So this has gone to 2 and this 2 has gone to 0. Okay, that's what I've shown here. So this is 2 and this is 0. Now immediately to analyze the circuit, we will start and see which node, either this node is going to change or this node is going to change. So initially, if to begin with, this node here is at 5 volts and this node here is at 0 volts. Immediately we can see this PMOS is cut off, this NMOS is cut off, sorry, and this PMOS is also cut off, right? Its VGS is 0, so both these devices are cut off. So they won't conduct, so this output 0 is going to remain constant. It's not going to change as of now. When will it change? Input is fixed, so NMOS can't do anything. This node has to be charged. So because it has to be charged, all the current has to come from PMOS. So when the VGS of the PMOS becomes greater than, or VSG becomes greater than mod VTP. Let's assume mod VTP is 1 volt. Right now this node is at 5. This PMOS is cut off because VDS of the PMOS is 0, because source is at 5, drain is at 5, it's cut off. Now the moment your NMOS gate is at 2 volts, this will start conducting current and it will start discharging this cap. The moment it discharges this cap, this node voltage will go lower. Many things are happening here now. This PMOS is starting to conduct. This PMOS is slightly, because it will not conduct until it goes to 4 volts, but it's slightly going into weak inversion region. Now, but this PMOS, this has a huge VGS and its VDS is slightly increasing, so it will start charging. So there are, if you look at this node, the output node, I've drawn it separately here. There are two devices. PMOS is trying to charge it, NMOS is trying to discharge it. Initially, NMOS is having a huge VGS and its VDS is also very huge because it's full VDS of 5 volts here. So it's going to be in saturation region and it's going to, IN is going to be greater than IP. So it's immediately going to discharge this node. But as soon as you start discharging this node, the PMOS starts conducting and the current starts increasing. So there are two candidates who are trying to affect this node voltage. PMOS is trying to charge it, NMOS is trying to discharge it. And for this node voltage to go lower, you have to guarantee NMOS current is greater than PMOS current. So generally, if you want to size the device, we will ensure that the size of the NMOS is much greater than the size of the PMOS. Okay, this is because I'll come to the discussion in a few moments, but let me just keep this point in mind. The NMOS current has to be greater because NMOS, the path of the input to the output, right? The path for the input to the output is through these NMOS devices. The information of the input is contained in the NMOS devices. The load is just a latch. Okay, it's just a cross-coupled PMOS device. It's just a latch. Latch will just store its value. Whatever value it was initially having, it will just store it. So the input disturbance that's coming through the NMOS should be strong enough that they should disturb the latch and reverse their polarity. So that's why I have to ensure that the NMOS is strong enough to disturb the latch operation. So therefore, NMOS should be sized stronger than the PMOS. Okay, so now this has happened. We have done the sizing. So I'll just assume that and go to the operation of the circuit. So the output node is now discharging. One of the output nodes is discharging. Other node is just staying at 0. So I'm plotting this node voltage here. From 5 volts, it starts to discharge and it reaches 4 volts. The moment it reaches 4 volts, the other PMOS starts conducting. Now the latch operation kicks into action. The moment the other PMOS starts conducting, you have a regenerative feedback. So that is equivalent to 2 CMOS inverters connected back to back. So that's what I've shown here. Let's assume you have 2 CMOS inverters which are connected back to back, which is what I've shown here. Initially, both of these nodes are at, say, some common mode, some switching threshold voltage. I slightly displace this node by delta V volts. This CMOS inverter with a gain of minus A will amplify to minus A times delta V. Then this inverter will amplify to minus A square times delta V. So it will be plus A square times delta V. So this node is becoming more positive. This is becoming more negative. It's like a regenerative feedback or positive feedback. Until this node voltage reaches VDD. It will not stop. It will keep on amplifying and so on. So that's the regenerative action or the action of a latch. So this latch action starts kicking in when the other PMOS starts conducting. Until then, only one PMOS was conducting, other PMOS was cut off. So there was no positive feedback. The moment this happens, so now on one side of the PMOS, if you see, it's connected here. The VGS of this PMOS is increasing because this is at VDD. This node voltage is going lower. So this VGS increases. And this node voltage is now starts to increase because this PMOS will now conduct and it will start charging this node. As this node voltage increases, this PMOS's VGS decreases. If this PMOS's VGS is decreasing, NMOS now is more powerful to keep pulling this node to 0 because NMOS doesn't have to fight the PMOS anymore because its VGS is decreasing. So it will keep pulling it to ground. So this node voltage keeps going further lower, now even more faster. As this happens, this node voltage starts rising and rising and rising, and when it reaches 4 volts, this PMOS is cut off. When this PMOS is cut off, now you have just NMOS discharging this node. NMOS will pull this node to 0 volts. And when this node is pulled to 0, your PMOS gets the full VGS and it will charge this node to 5 volts. Okay, so now we were able to push this node to 5 volts. So in the steady state, this node voltage comes to 0. Okay, and the other node voltage comes to 5 volts. Okay, so that's what I've shown here. The same circuit, I just replace the supply with from 5 volts to 20 volts. I'll get the same operation. Okay, I just have to size my NMOS stronger and I'll get 20 volts. So I've connected this node at 2 volts, say this node is at 0 volts. Then in the steady state, this will come to 0 and this node will go to 20 volts. Now immediately you can see that the static power dissipation is 0. All the devices are cut off. This device has no VGS. VGS is less than VT. This device's VDS is 0. So drain and source are at 0 volts. VDS is 0. This device is cut off again because VGS is 0. This device is cut off because VDS for this device is 0. So all the devices are turned off, so static power dissipation is 0. So that's it. So this is a simple PMOS cross-coupled latch. A simple CMOS level shifter circuit with a PMOS cross-coupled load or a PMOS latch as a load. So that's what I've drawn here. If you feed a 0 to 2 volt input, you'll get a 0 to 20 volt output. Now, when I was talking about the discharging path, I said the cross-coupled latch has only the ability to pull up the node to VDD. It has the ability to pull up a node to VDD. Discharging is not controlled by the PMOS. Discharging is entirely controlled by NMOS. Now what I'll do is, when the NMOS is, let's say initially it was at 20 volts and it was discharging it, what I'll do is I'll just add a PMOS device in the path, in the discharging path, and see what happens. Now I'm going to connect the gate of the PMOS at a voltage of VL minus mod VTP. Now this node is getting discharged. So from 20 volts, it keeps decreasing and decreasing. When it reaches a value of VL volts, what will happen is that even though NMOS is conducting, it's fully conducting and ready to receive the current, the series PMOS device is turned off because its VGS becomes 1 mod VTP, right? So gate is at VTP lower, so VGS becomes just equal to 1 mod VTP, so it stops conducting. So you're cutting off the discharge path. So by adding this PMOS, all I'm doing is I am just cutting off the discharge path when the node voltage reaches a value of VL. So instead of reaching 0 volts, 20 to 0, it will stop at 22 VL volts. So that's all this circuit is doing. It's just restricting the VL voltage, the lower voltage. In the example given, this lower voltage was given to be 15 volts. So I've just added 2 PMOS devices in series. If this is 15 volts, then you can expect the output voltage to go to a minimum value of 16 volts. See, this input is 2, this input is 0. So ideally I would expect this to go to 20. This cross-coupled latch will pull this node to 20. No problems there. But this node discharging is controlled by NMOS. So that will stop when this node voltage reaches 16 volts. So it will not go to 20 to 0. So now you have a input signal which is going from 0 to 2 volts, an output signal that goes from 16 volts to 20 volts. So that's the application of this. This is actually limiting your lower voltage. So you can program whatever your low voltage you want it to be. Okay, so that's the application of the circuit. Now immediately you can see the static power dissipation is 0 here also, right? So once a CMOS latch regenerates, the only problem you have to worry about is that, actually, if any device is conducting by adding this PMOS, again, that's just to verify static power dissipation being 0. So immediately you can see what happens to the cross-coupled latch. Cross-coupled latch, this VGS is 0, so this is cut off. The other PMOS has a full VGS, but its VDS is 0, so that is also cut off. Okay, so since PMOS upper path is cut off, you can automatically see that there is no static power, there is no path from supply to ground. Okay, and you can immediately see this device is cut off, and since this device is cut off, there is no current flowing through this device. Okay, and if this is at 20 volts, it will there is no discharging path. If this is at 20 volts, this PMOS can still conduct, and it will come to a cutoff region when this node voltage reaches 20 volts. When this node voltage reaches 20, the VDS of this PMOS goes to 0. Okay, so it will stop there. And this PMOS, on the other hand, when it reaches 16 volts, this device is cut off. Okay, because your VDS itself, your VGS itself goes to, your VGS itself is 0, and it's like an open switch. So if this is 16, all the voltage will drop across this device, and this will be at 0 volts. It's like an open switch, right? So when you have an open switch, it's like an open circuit. So all the 16 volts will drop across this, and the NMOS will have only 0 volts across it. VDS is 0 for this device. Okay, so all the devices are cut off, so this is still a static power dissipation is 0. So in the same way, you can think about, can you limit the upper side voltage? If I want to limit the lower side voltage, I have to use PMOS. To limit the upper side voltage, all I need to do is just add NMOS on the cross-coupled, at the output of the cross-coupled inputs, cross-coupled CMOS pair, cross-coupled PMOS pair. So this node voltage can go to 20. 0 is anyways fine. Okay, 0, we can worry about the node 0 later. 0 is determined by the discharging path. This node goes to 20, but this node voltage, the NMOS will not let this node go more than VH. Once this node is charged to VH volts, this NMOS device will be cut off. Okay, so I can limit the upper voltage also. You can think about it, it's very simple. So that's what I've just modified the circuit and drawn here. If the gate here is connected to VH plus mod VGS, mod VTN, I'm sorry, this is supposed to be VH plus mod VTN, then the maximum voltage the output can go to will be VH itself. And if the gate is for a PMOS device, if you connect the lower path to VL minus mod VTP, that PMOS device is controlling the discharge path. Okay, the minimum voltage it can go to is VL. So I can now restrict the voltage levels between some VL and VH using this, and also at the same time guaranteeing you a zero static power dissipation. Okay, so you can immediately analyze this circuit the way I had done for the other part of the circuit. So it's very simple. I won't do this, so you can do it as an exercise for yourself. Okay, so that's it. Thank you. You can please don't feel free to email me any questions you have, and I may not have time to reply to every question, but once in a while if I find an interesting question, I'll definitely try to make a video on it. Thank you.